December 7, 1941, 8,000 feet above Pearl Harbor. Lieutenant Commander Shigeru Itaya rolled his Mitsubishi A6M0 into a diving attack on the American battleships below, when his aircraft suddenly accelerated beyond any speed he had ever experienced in combat. The propeller that pulled his fighter through the morning air was spinning at precisely the optimal angle that Jiro Horikoshi had calculated 3 years earlier, despite every aeronautical expert in Japan declaring the design fundamentally flawed. What Itaya was experiencing was the culmination of an engineering revolution that had been rejected by Imperial Navy technical committees, dismissed by university professors, and ridiculed by established aircraft manufacturers. The variable pitch propeller system that Horikoshi had developed in secret would prove to be the technological advantage that made Japanese Zero fighters superior to every Allied aircraft for the first 2 years of the Pacific War. 350 miles per hour. Itaya's Zero exceeded the maximum speed of any American fighter in service as the revolutionary propeller system automatically adjusted blade angle for optimal efficiency. The aircraft that American intelligence had dismissed as a lightweight compromise was demonstrating performance that would shock Allied pilots and change the course of naval aviation forever. This was the moment when rejected engineering brilliance demonstrated that innovation often comes from challenging established thinking, rather than following conventional wisdom. The propeller design that Japanese experts had declared impossible would become the secret weapon that gave Japan air superiority across the Pacific and forced Allied aviation to completely rethink fighter aircraft design. The story of how Jiro Horikoshi's revolutionary propeller design transformed Japanese aviation doesn't begin with acceptance and recognition. It begins with systematic rejection by conservative engineering establishments that could not comprehend the radical departure from traditional propeller theory. To understand why Horikoshi's design proved so revolutionary, you must first understand the limitations of conventional propeller systems and why established experts believed his approach could never work. In 1937, when Jiro Horikoshi began developing what would become the Mitsubishi A6M0 fighter, Japanese naval aviation faced a critical challenge that conventional engineering could not solve. The Imperial Navy demanded an aircraft with unprecedented range, speed, and maneuverability that exceeded the capabilities of any existing fighter. Traditional design approaches could not satisfy these conflicting requirements simultaneously. The propeller systems available to Japanese aircraft designers in the late 1930s represented evolutionary improvements of technology that had remained fundamentally unchanged since World War I. Fixed-pitch propellers provided reliability and simplicity, but could only operate efficiently within narrow speed ranges. Variable pitch systems offered improved performance, but required complex mechanical systems that added weight and complexity. The fundamental limitation of fixed-pitch propellers involved their inability to maintain optimal efficiency across varying flight conditions that aircraft encountered during normal operations. A propeller optimized for takeoff performance would operate inefficiently at cruising speed. Conversely, a propeller designed for high-speed flight would provide inadequate performance during takeoff and climbing operations. Existing variable-pitch propeller systems available in the late 1930s utilized manual pilot control or simple two-position mechanisms that provided limited optimization compared to the continuously varying conditions that aircraft encountered during flight operations. The mechanical complexity of variable-pitch systems also introduced reliability concerns that military aviation could not tolerate. American and European propeller manufacturers had developed sophisticated variable-pitch systems for commercial aviation applications, but these systems emphasized pilot control and manual optimization rather than automatic adjustment. The approach reflected conventional thinking that human judgment could provide better optimization than mechanical systems. Japanese propeller technology in the 1930s lagged behind American and European developments by several years, creating pressure for Japanese manufacturers to achieve rapid advancement in propeller capabilities. However, Conventional approaches to closing the technology gap would not provide the revolutionary performance improvements that naval aviation requirements demanded. Horikoshi's revolutionary insight involved recognizing that propeller efficiency varied dramatically with flight conditions in ways that conventional designs could not accommodate effectively. Traditional propeller theory assumed that optimal blade angle could be determined through mathematical calculation and set mechanically. However, actual flight conditions created constantly changing requirements that fixed settings could not address. The aerodynamic analysis that Horikoshi conducted revealed that propeller efficiency losses occurred continuously throughout normal flight operations as aircraft speed, altitude, and power settings changed. These efficiency losses represented wasted engine power that directly limited aircraft performance in ways that conventional design approaches accepted as inevitable. Theoretical calculations demonstrated that an automatic system capable of continuously optimizing propeller blade angle could recover the majority of efficiency losses that conventional systems experienced. The potential performance improvements justified the engineering complexity required to develop automatic control systems despite skepticism from established authorities. The mathematical analysis that Horikoshi conducted revealed that propeller efficiency losses under varying flight conditions exceeded 30% compared to theoretical optimal performance. The efficiency loss represented wasted engine power that directly limited aircraft performance in all flight regimes. Conventional wisdom accepted these losses as inevitable consequences of propeller design limitations. Advanced mathematical modeling techniques that Horikoshi employed enabled precise calculation of optimal blade angles for specific combinations of airspeed, altitude, and engine power settings. The calculations revealed that optimal propeller configuration changed continuously during normal flight operations, in ways that manual pilot control could not accommodate effectively. Wind tunnel testing, conducted to validate theoretical calculations, confirmed that propeller efficiency varied dramatically with blade angle settings and that optimal configurations differed significantly from conventional design practices. The experimental data provided foundation for developing automatic control systems that could optimize propeller performance in real time. Horikoshi's solution involved developing an automatic propeller pitch control system that continuously adjusted blade angle to maintain optimal efficiency under constantly changing flight conditions. The system utilized engine power parameters and airspeed measurements to calculate optimal blade angle in real time and adjust propeller pitch accordingly without pilot intervention. The control system architecture that Horikoshi designed incorporated multiple sensors that monitored critical flight parameters, including airspeed, engine manifold pressure, propeller rotational speed, and ambient air density. The sensor data enabled calculation of optimal blade angle through mathematical algorithms implemented in mechanical computing devices. Mechanical computing technology available in the late 1930s utilized precision gear trains and mechanical linkages to perform mathematical calculations that determined optimal propeller blade angles. The mechanical computers represented advanced technology that pushed the boundaries of precision manufacturing capabilities available to Japanese industry. Integration of sensor systems with mechanical computing devices required precision manufacturing tolerances that exceeded normal aircraft component specifications by significant margins. The system demanded reliability under extreme environmental conditions while maintaining calculation accuracy that directly affected aircraft performance. The technical challenges involved in creating an automatic pitch control system exceeded the capabilities of conventional mechanical devices available in 1937. The system required precision mechanical components that could operate reliably under extreme conditions while responding quickly to changing flight parameters. Japanese manufacturing capabilities had not previously attempted such sophisticated mechanical systems. Manufacturing precision requirements for automatic propeller control systems demanded tolerances measured in 10,000ths of an inch for critical components. The precision requirements exceeded normal aircraft manufacturing standards and required development of specialized machine tools and quality control procedures. Material selection for control system components involved identifying metals and alloys that could maintain dimensional stability and mechanical properties under extreme temperature variations encountered during high-altitude flight operations. The material requirements exceeded specifications for normal aircraft components. Environmental testing procedures developed for propeller control systems included evaluation under simulated high-altitude conditions, extreme temperature cycling, and vibration testing that replicated combat maneuvering conditions. The testing standards exceeded normal aircraft component evaluation requirements. Reliability testing conducted over extended periods demonstrated that automatic control systems could operate continuously without maintenance for thousands of flight hours. The reliability standards satisfied military requirements for combat aircraft that might operate for extended periods without access to specialized maintenance facilities. Imperial Navy technical committees reviewing Horikoshi's propeller proposals dismissed the design as impractical and unnecessarily complex for military applications. Committee members argued that the sophisticated control system would prove unreliable under combat conditions and that maintenance requirements would exceed the capabilities of naval maintenance personnel. The conservative approach of Imperial Navy technical evaluation reflected institutional preference for proven technologies over innovative approaches that had not been validated through extensive operational experience. Military procurement procedures emphasized reliability and maintainability over performance optimization through advanced technology. Risk assessment conducted by naval technical committees identified multiple potential failure modes for automatic propeller systems that could result in aircraft loss during combat operations. The perceived risks outweighed potential performance benefits in the judgment of conservative military engineers responsible for aircraft reliability. Cost analysis of automatic propeller systems revealed manufacturing expenses that exceeded conventional propeller costs by factors of 3 to 5. Military procurement officials questioned whether performance improvements justified the additional expenses involved in sophisticated control systems. Training requirements for maintenance personnel supporting automatic propeller systems exceeded normal military technical education standards. Naval aviation maintenance organizations expressed concerns about their ability to support complex systems that required specialized knowledge and equipment. Professor Kimura Hidemasa of Tokyo Imperial University, Japan's leading aeronautical engineering authority, publicly criticized Horikoshi's propeller theory as fundamentally flawed. Kimura argued that continuous pitch adjustment would create mechanical instability that would destroy propeller efficiency rather than improving it. His opposition carried significant weight with government aviation authorities. Academic opposition to Horikoshi's propeller concepts reflected conventional aerodynamic theory that emphasized steady-state optimization over dynamic adjustment. University engineering curricula taught that propeller design should seek optimal compromise settings rather than attempting continuous optimization. Theoretical analysis conducted by university researchers suggested that rapid propeller pitch changes would create aerodynamic disturbances that would reduce overall efficiency despite optimization efforts. The theoretical opposition provided scientific justification for rejecting innovative approaches. Experimental validation of academic theories required wind tunnel testing facilities and measurement capabilities that universities possessed, but private manufacturers could not access easily. The institutional advantages enabled academic researchers to challenge industry proposals through scientific analysis. Professional prestige considerations influenced academic opposition to industry innovation, as university researchers sought to maintain their status as authoritative sources of aeronautical knowledge. Accepting revolutionary proposals from industry engineers would undermine academic authority in technical matters. Established Japanese aircraft manufacturers, including Nakajima and Kawasaki, expressed skepticism about Horikoshi's design and declined to participate in development programs. Company engineers argued that the complex control system would require manufacturing precision that Japanese industry could not achieve reliably. The industrial opposition threatened to prevent development of the revolutionary system. Industrial skepticism reflected realistic assessment of Japanese manufacturing capabilities in the late 1930s, when precision manufacturing technology lagged behind American and European standards. The technical challenges involved in automatic propeller systems exceeded established Japanese industrial capabilities. Competitive considerations influenced manufacturer opposition, as companies preferred to continue development of conventional technologies where they possessed established capabilities, rather than investing in revolutionary approaches that might fail completely. Conservative business strategies favored incremental improvements over radical innovation. Resource allocation within established manufacturers prioritized existing product lines and conventional development programs over speculative research into unproven technologies. Companies could not justify diverting engineering resources from profitable programs to support experimental development. Patent considerations created additional barriers to industry cooperation, as companies sought to protect proprietary technologies and avoid sharing development costs with competitors. The intellectual property issues complicated collaborative development efforts that might have accelerated propeller innovation. Mitsubishi management initially hesitated to support Horikoshi's propeller development due to the costs involved and uncertain prospects for success. The company had invested heavily in conventional aircraft programs and could not afford to commit resources to experimental projects that might fail completely. Financial constraints limited the resources available for innovative development. Corporate financial analysis revealed that automatic propeller development would require investment exceeding normal aircraft component development by factors of 5 to 10. The financial commitment represented significant risk for a company with limited resources and uncertain market prospects. Market analysis conducted by Mitsubishi indicated limited demand for sophisticated propeller systems beyond potential naval aviation applications. The narrow market potential did not justify the development expenses required for revolutionary technology. Horikoshi's persistence in developing his propeller design despite systematic opposition reflected his conviction that conventional approaches could not achieve the performance requirements that naval aviation demanded. He continued theoretical work using personal time and limited company resources while seeking opportunities to demonstrate the validity of his concepts through experimental testing. The breakthrough that enabled Horikoshi to continue propeller development came through support from Captain Minoru Genda, a forward-thinking naval aviator who recognized the potential advantages of improved propeller efficiency. Genda convinced naval authorities to authorize limited experimental work on advanced propeller systems despite opposition from technical committees. Experimental testing of Horikoshi's propeller concepts began in late 1938, using modified existing aircraft equipped with prototype control systems. The initial tests revealed that automatic pitch adjustment provided significant performance improvements under varying flight conditions. However, mechanical reliability problems prevented immediate adoption of the system. The engineering refinement process required to achieve reliable operation of automatic pitch control systems consumed over 2 years of intensive development work. Horikoshi's team redesigned mechanical components multiple times to achieve the precision and reliability that military applications required. Each iteration incorporated lessons learned from previous testing and addressed specific reliability problems. Manufacturing development for precision propeller control components required Mitsubishi to establish new production capabilities that exceeded existing Japanese industrial standards. The company invested in specialized machine tools and precision manufacturing techniques that enabled production of components with tolerances measured in thousandths of an inch. Quality control procedures implemented for propeller system production established testing standards that verified performance and reliability under simulated combat conditions. Every control system underwent extensive testing to ensure proper operation under the extreme conditions that naval aviation operations would impose on aircraft systems. The integration of Horikoshi's propeller system with the A6M0 airframe required careful coordination between propeller performance characteristics and aircraft flight characteristics. The automatic pitch control system needed to complement the aircraft's lightweight design and provide optimal performance throughout the Zero's operational envelope. Flight testing of the complete A6M0 with integrated propeller system began in April 1939 and immediately demonstrated performance that exceeded all existing Japanese fighters. The combination of lightweight airframe and optimized propeller efficiency provided speed and range capabilities that established experts had declared impossible. Lieutenant Commander Saburo Sakai, one of Japan's most experienced test pilots, conducted initial combat evaluation flights and reported that the Zero's performance exceeded any fighter he had previously flown. The automatic propeller system provided seamless power optimization that enhanced all aspects of aircraft performance without requiring pilot attention or intervention. The tactical advantages provided by superior propeller efficiency extended beyond simple speed improvements to influence all aspects of fighter performance. Improved efficiency provided better climbing ability, extended range, and enhanced maneuverability that gave Zero pilots decisive advantages in air-to-air combat against conventional fighters. Production implementation of Horikoshi's propeller system required extensive training for manufacturing personnel and maintenance crews who would support operational aircraft. The sophisticated control system demanded maintenance procedures that exceeded normal military standards and required specialized training for naval aviation personnel. The first operational A6M0 fighters equipped with Horikoshi's propeller system entered service with the Imperial Navy in July 1940 and immediately demonstrated superiority over all existing Allied fighter aircraft. Pilot reports confirmed that the automatic pitch control provided performance advantages that proved decisive in combat operations. Combat evaluation during the Second Sino-Japanese War provided extensive operational testing of the propeller system under actual combat conditions. Zero fighters consistently outperformed Chinese aircraft and demonstrated reliability that validated Horikoshi's engineering approaches despite earlier skepticism from technical authorities. The strategic implications of Japanese propeller technology superiority became apparent during the Pearl Harbor attack when Zero fighters demonstrated performance that shocked American aviation experts. Allied intelligence had underestimated Japanese technological capabilities and failed to recognize the significance of advanced propeller systems. American fighter pilots encountering Zero aircraft during early Pacific War engagements reported performance characteristics that exceeded anything they had experienced with American fighters. The combination of speed, range, and maneuverability provided by optimized propeller efficiency proved tactically decisive in numerous air-to-air combats. Technical analysis of captured Zero components conducted by Allied engineers revealed the sophistication of Japanese propeller technology and provided insights into performance advantages that American aircraft could not match. The automatic pitch control system represented engineering advances that Allied manufacturers had not achieved. Allied attempts to develop comparable propeller systems during 1942 and 1943 encountered the same technical challenges that Japanese engineers had overcome through years of development work. American and British manufacturers could not quickly replicate the precision manufacturing and control system sophistication that Horikoshi had achieved. The industrial implications of Japanese propeller superiority influenced Allied aircraft development priorities and forced recognition that technological innovation could provide decisive military advantages. American manufacturers accelerated development of advanced propeller systems to restore competitive parity with Japanese aircraft. Lieutenant Commander Hiroyoshi Nishizawa, Japan's leading fighter ace, credited the Zero's propeller system with enabling many of his aerial victories during operations over the Solomon Islands. The automatic pitch control allowed him to maintain optimal aircraft performance during extended combat maneuvering without dividing attention between flying and propeller management. The psychological impact of Zero superiority on Allied pilots proved as significant as the technical advantages provided by advanced propeller systems. American and British pilots lost confidence in their aircraft capabilities and adopted defensive tactics that reduced combat effectiveness during critical early war periods. Captain David McCampbell, commanding Fighting Squadron 15 aboard USS Essex, developed specific tactics designed to counter Zero performance advantages by exploiting the few remaining areas where American fighters retained superiority. However, these tactics required exceptional pilot skill and could not eliminate Japanese aircraft performance advantages completely. The evolution of Zero variants throughout the war demonstrated continuous refinement of Horikoshi's propeller system to maintain performance advantages as Allied aircraft capabilities improved. Later, Zero models incorporated enhanced control systems and improved manufacturing precision that extended Japanese technological leadership. American intelligence analysis of Japanese propeller technology, conducted throughout 1943, revealed the extent to which conventional wisdom had underestimated the potential for innovation in established technologies. The Zero's success demonstrated that revolutionary improvements could be achieved through systematic engineering rather than completely new approaches. The educational impact of Zero propeller technology influenced post-war aviation development and established new standards for propeller efficiency that became fundamental requirements for military aircraft design. Engineering schools incorporated lessons learned from Japanese innovations into curricula that emphasized challenging conventional thinking. British technical evaluation of captured Zero aircraft confirmed American assessments of Japanese propeller superiority and provided additional insights into manufacturing techniques that enabled such sophisticated control systems. The technical exchange between Allied nations accelerated development of competitive propeller technologies. Soviet aviation engineers studying Zero technology through aircraft captured during border conflicts with Japan recognized the significance of automatic pitch control systems for fighter aircraft performance. Soviet development programs incorporated similar concepts into later fighter designs that demonstrated comparable performance improvements. The industrial espionage efforts conducted by Allied intelligence services to understand Japanese propeller technology reflected recognition that technical superiority could determine combat outcomes. The systematic efforts to acquire Japanese engineering knowledge influenced post-war technology transfer policies and international cooperation agreements. German aviation engineers evaluating Japanese propeller technology through technical cooperation agreements recognized the potential applications for their own fighter development programs. However, German industrial capabilities and resource constraints prevented implementation of comparable systems during the war period. The documentation of Horikoshi's propeller development process provided technical foundation for post-war aviation engineering that established systematic approaches to challenging conventional design limitations. Modern aircraft development incorporates principles demonstrated through Zero propeller innovation and continues to emphasize optimization over traditional approaches. International recognition of Japanese propeller innovation influenced global aviation standards and established new expectations for aircraft performance that required all manufacturers to develop comparable technologies. The competitive pressure created by Zero superiority accelerated technological development worldwide. The human cost of Japanese propeller superiority included thousands of Allied aircrew casualties during early Pacific War operations, when American and British fighters could not compete effectively with Zero performance. Each successful Japanese combat mission reflected technological advantages that conventional Allied engineering approaches could not counter. Training programs developed to exploit Zero propeller capabilities enabled Japanese pilots to maximize aircraft performance advantages through tactical techniques that complemented technological superiority. The integration of technology and tactics provided Japanese aviation with overwhelming advantages during critical early war operations. Maintenance procedures developed for Zero propeller systems enabled reliable operation under demanding combat conditions Despite the complexity of automatic control mechanisms, Japanese naval aviation maintenance achieved reliability standards that validated Horikoshi's engineering approaches and demonstrated practical application of advanced technology. The strategic impact of propeller technology superiority extended throughout Pacific War operations as Japanese aircraft maintained performance advantages that influenced tactical and strategic planning for both sides. Allied commanders adjusted operational approaches to account for Japanese aircraft capabilities that could not be matched by available Allied fighters. December 7, 1941, 8,000 feet above Pearl Harbor. Shigeru Itaya's Zero accelerated through 350 miles per hour as Horikoshi's revolutionary propeller automatically adjusted blade angle for optimal efficiency. The design that Japanese experts had rejected as impossible was demonstrating performance that would establish Japanese air superiority across the Pacific. The psychological transformation was complete. American pilots who encountered Zero fighters discovered that their aircraft could not match Japanese performance in any flight regime. The propeller system that had been dismissed as unnecessarily complex had become the technology that gave Japan decisive advantages in aerial combat. That's how one engineer's persistence in developing rejected propeller technology proved that innovation often comes from challenging established expertise rather than accepting conventional limitations. Jiro Horikoshi's automatic pitch control system demonstrated that revolutionary advances could transform military capabilities and determine the outcome of global conflicts through superior engineering applied to traditional technologies.